In this lecture, we're going to start looking into recursion and recursive functions. We will look at divide and conquer as an algorithm design strategy and how to implement divide and conquer algorithms using recursion. So it is possible for a function to call itself. This is called a recursive function. And some problems are very easily solved using recursion. The strategy by which recursion is used to solve a problem is called divide and conquer. Here is the general idea. You've got a problem P, which is very big to solve. So what we do is we divide the problem into subproblems called P1, P2, Pn. So you have to have at least two such subproblems. Each subproblem is a smaller version of the original problem. So P1, P2, and Pn has to have a smaller scale compared to P, but they have to have the same type in terms of formulation. So P1 is the same formulation of the original problem, but has a smaller scale. P2 is the same and Pn is the same. This is called dividing the problem or recursive formulation of the problem. Now we recursively solve each of these subproblems. That's called the conquer part. So when you recursively solve this P1, which is again a problem of the same type as P, but has a smaller scale, we will do the same thing, meaning that P1 will now be divided into subproblems called P11, P12, P1n, and that applies to every other subproblem. So P2 will be divided into subproblems called P21, P22, P2n, and the last subproblem Pn will be divided into subproblems called Pn1, Pn2, and Pnn. Eventually, each of these subproblems will be divided further, and as we divide these problems further and further, eventually we are going to reach a point where the problem is so small that we don't have to divide it any further. The solution is obvious. These are called base cases or stopping conditions. Now that we have the solution to these tiny sub problems, the merge part starts. So we have conquered all the solutions to these subproblems. We now backtrack from the recursion, going back up now, merging the solution to these subproblems to obtain the solutions to the bigger problems. Eventually, we are going to come to the original first recursive call, P, where we are going to obtain the solution to P1, the solution to P2, and solution to Pn. So what remains is merging the solution to these subproblems to obtain the solution to the original problem P and returning it from the function. Here is the general template for every recursive function that you're going to implement. You have a function solve, a recursive function solve that takes a problem P. At the top of your recursive function, you will always write the code for the base cases or stopping conditions, meaning that you first check if P is a base case problem, meaning that if the problem is very small, then the solution is obvious. You don't have to divide it any further. So in that case, we just return the solution immediately without going into the body, the rest of this template solve function. Otherwise, we now have to divide this problem into subproblems. Let's call them P1, P2, Pn. So divide P into P1, P2, Pn, each of smaller scale. Remember, each of these subproblems have to have the same type as the original problem P, but will have smaller scale. That means that if our black box function solves the bigger problem P, it definitely solves a smaller problem of the same type. So we can just call solve to get a solution to P1, and we can call solve to get a solution to P2, and so on and so forth. So now we have solution to these subproblems. Let's call them S1, S2, and Sn. So what remains now is we need to have a merge step at the end to somehow merge the solution to these subproblems to get the solution to the original problem. And that's what we returned at the end. Bottom line is every recursive function that you're going to implement from now on will have this general template. So solve is the recursive function that takes a problem P. At the top, you write the code for the base cases. Otherwise, you have the recursive formulation of the problem. Divide the problem into subproblems P1, P2, and Pn. Now you recursively call the same function solve to get a solution to this subproblem. Let's call them S1 and Sn. Eventually, you're going to have a merge step to merge the solution to these subproblems obtain the solution to the bigger problem and return it at the end. Let's now look at our first problem. We would like to compute the summation of the numbers from 1 to n recursively. Obviously, iteratively, you can simply write a loop to compute the sum of the numbers from 1 to n. But here is the recursive function we would like to implement. So a function sum that takes n and computes 1 plus 2 plus 3 up until n. Let's first identify the base case for this problem. The base case is if n is equal to 1, then we know that the sum of the numbers from 1 to 1, remember, if n is equal to 1, this is 1, then the sum of the numbers from 1 to 1 is 1. So we don't have to divide the problem any further. This is our base case or stopping condition. Let's now recursively formulate the problem. So here is how we can recursively formulate the problem. Remember that we are trying to compute the sum of the numbers from 1 to n, and we can write it as 1 plus 2 plus dot dot plus n minus 1 plus n. And you can see that in order to compute the sum of the numbers from 1 to n, you need to first compute the sum of the numbers from 1 to n minus 1. So you could recursively formulate this as sum of n minus 1. Remember, sum of the numbers from 1 to n minus 1 is the subproblem that is of the same problem as the original problem but has a smaller scale. So the size of the original problem is n, size of the subproblem is n minus 1. That means we can make a recursive call to our function sum to compute the sum of the numbers from 1 to n minus 1. And now the merging is very simple. All we have to do is add n to the solution of the subproblem to compute the solution to our original problem, which is of size n. And here is the recursive function that implements this code. This is example1.cpp in our example code. Again, remember the template that I gave you. So we are trying to write this recursive function sum that takes a problem of size n and tries to compute the sum of the numbers from 1 to n. At the top of our function, at the beginning, we have to write the code for the base case or the stopping condition. Remember, the base case or the stopping condition for our recursive function is if n is equal to 1, meaning if the size of the problem is 1, then the solution is 1. So the sum of the numbers from 1 to 1 is 1. So we immediately return the solution without going into the rest of the recursive function. So this is our base case or stopping condition. Otherwise, we now divide and conquer the problem. Remember, the recursive formulation of the problem was we first compute the sum of the numbers from 1 to n minus 1, which is the same problem but has a smaller scale. So the original problem has a size of n, but this subproblem has a size of n minus 1. So this solve function, this sum function, has to, if it is solving a bigger problem of size n, it must solve a smaller problem of the same type, n minus 1. So now we get the solution to this subproblem. Let's call it partial sum. The merge step is very simple. All we have to do is we have to add n to the partial sum to obtain the solution to the original problem. And here is a main function that makes a call to sum to compute the sum of the numbers from 1 to 4. Let's see how this is executed. This is called the recursion tree for sum. So we start at main, and this is the first statement we are going to execute. We are going to say x is equal to sum 4. We are basically making a call to function sum with a parameter of 4, which indicates the size of our problem. So here is what we are doing. We're saying x is equal to sum 4. So when we make a call to this function, the control is going to jump from here to the first statement in sum, passing n, which is 4, as an argument to this function. So we are now inside sum 4. So let's just trace this through. So we are at the beginning of this code. Is n equal to 1? Are we at the base case yet? No, because n is equal to 4. So n is not equal to 1. So we continue and execute partial sum is equal to sum n minus 1, meaning 3. So remember, n is 4 at this point. N minus 1 is 3. So we are going to make a call to sum, again, recursively with a parameter, with an argument of 3, meaning that we have now reduced the size of our problem from 4 to 3. And we are asking the sum function to find the solution to some of the numbers from 1 to 3. So we are going to make another recursive call to sum3. And now we are again at the beginning of this function, but the parameter, the value of the parameter n is 3 at this point. Again, with the first statement is the base case, is n equal to 1? The answer is no. So we again continue and execute this statement, which says partial sum is equal to sum n minus 1. This time n is equal to 3, so n minus 1 is equal to 2. So we are going to execute the statement partial sum is equal to sum 2. Then, because we are making a call to function sum2, the control again jumps back to the beginning of the function, but this time the value of the parameter is 2. So we enter the function again and check the base case. If n is equal to 1, the answer is no. So we continue and execute partial sum is equal to sum n minus 1, because n is equal to 2 this time, so this will be sum 1. So this is the statement we are going to execute. Partial sum is equal to sum 1. Again, this is a function call with a parameter value of 1. We are going to again jump to the beginning of the function, but this time the value of the parameter n is 1. When we enter the function, we are now hitting the base case, as you can see, because the value of the parameter at this point is 1. If n is equal to 1, that is true, n is equal to 1, so we return the solution, which is 1. Again, we have started with a very big problem of size 4. At each step, we have reduced the problem size by 1, and eventually we have hit the base case or the stopping condition, which simply returns the solution of 1. When we return from sum 1, we are going to eventually return to partial sum n minus 1, which was in the context of sum 2. So now the partial sum, the local variable, in the context of sum 2 will have a value of 1. And the execution continues. We are at this point. The execution continues into the merge step, which says return partial sum plus n. Remember, the value of n within the context of sum 2 is 2. The value of the partial sum is 1, which is what we obtained from the recursion. Now we're going to say 1 plus 2, which is equal to 3. And now we are back into the context of sum 3, and at this point, so partial sum we get the value that we are getting from the recursion, and that's 3. So the partial sum in the context of sum 3 will have a value of 3. The execution continues with the merge step, which says return partial sum plus n. Partial sum is 3, n is 3, so it is 3 plus 3, we are returning 6. We again go back to, when we return from recursion, we are backtracking. We return to the context of sum 4, which made the recursive call. So at this point, partial sum within the context of sum 4 will have a value of 6. The execution continues with return partial sum plus n, and that would be 6 plus 4, because the value of n is 4. The value of partial sum is 6, so that would be 6 plus 4 and 10. Now we are returning back into the context of main, which made the first recursive call. So x is equal to sum 4. So this sum 4 returns 10. The value of x would be 10, and that's going to be what we print on the screen. So let me actually execute this code on the VS Code. So let me come here. Let me go step by step so that you actually see that this is actually what happens. So we are in here, we are within main. We are making a call to sum with a value of 4. So we are getting into the function. So I'm doing F11 to get into the function. We are at the first statement of the function. Is n equal to 1? No, look at here. The value of n is 4. So we continue, we come here. Now we are again making a call to sum, but this time the size of the problem decreases by 1. So the n is 4 at this point. When I make a recursive call, the value of n minus 1 is 3. So again, control jumps back to the beginning of the function sum, but this time the value of the parameter is 3. So is it the base case? No, we come here. This time we are making another recursive call, and the value of n is 3 minus 1, 2. So we are again inside the first statement of sum. This is the recursive call. N is 2. Is it equal to 1? No. We continue. This time we are making another recursive call to sum, but the value of the parameter is 1 at this point. And we hit the base case. So that means we are going to return from here. And also I want you to observe the call stack at the bottom. So call stack is we are at the main, then we are making a first call, call to sum, where the value of the parameter is 4. Then that makes another recursive call with a parameter value of 3. That makes another recursive call where the parameter value is 2. And eventually we are at the base case where the value of the parameter is 1. So now we are going to return from the recursion. So we return, as you can see, we are back into uh, the next statement after this call. So the um, partial sum is 1, but the value of n is 2. So this is going to be 1 plus 2, 3. We return from this function. We go back to the context of sum 3. So we return here. The control continues with the next statement, which is merge. The partial sum is 3, n is 3. So we return 6. And we again return to the context of sum 4, where the partial sum is 6. The value of n is 4. We do 4 plus 6 plus 4, that's 10. And now we return to the context of main, which made the first call to function sum. Now the value of answer is 10, and we print that value on the screen, and we are done. So it says 1 plus 2 plus blah, 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 up to 4 is equal to 10. Let me also show you the call stack as we make these recursive calls. Initially, when your program starts executing, we are within the main function. So we only have the invocation frame for the main function, which has only one local variable, x. So x is equal to sum4. That's the recursive call, the function call we are going to make. So when we make a function call to 4, obviously you're going to allocate on the stack enough space for the parameter that has only one parameter, and it has one local variable called partial sum. So this is the invocation frame or call frame for sum4. Again, a space for the parameter n, which has a value of 4, and a space for the local variable partial sum, whose value is undefined at this point because we did not assign anything to partial sum yet. But when we come here, we're going to make sum 3. So we are making another recursive call to function sum with a value of 3. So that's sum 3. This time we are allocating space for the invocation frame of sum 3. So the value of the parameter n is 3. The value of the partial sum is still undefined. As you can see, each function call allocates a new function invocation frame on the stack. That's why these parameters and the local variables are different for each function call. They do not override each other. So we are inside the context of sum 3. That makes a call to sum 2. So that's another recursive call. So sum 2, now we have to allocate space for the parameter n and the local variable for the recursive function call of sum 2. And that's going to eventually make another recursive call to sum 1 with a parameter of 1. So now this time n is equal to 1. The value of the partial sum is undefined. And when we enter the function with a value of 1, we hit the base case and we return. So we return 1. So that means we are now backtracking from the recursion. We are going back up the recursion tree. So when we return, obviously we are going to return into the context of sum 3 into this line. So, sum 1, and change the value of the partial sum within the context of sum 2. So that means the value of partial sum within the context of sum 2 will be equal to 1 now. The execution continues with merge step. It says return partial sum plus 1. So this is partial sum is 1, n is equal to 2. Remember, we are in the context of sum 2 now. Partial sum is 1, n is equal to 2. So we add 1 plus 2, that's 3. We return from the recursion. And when we return, the local variables and parameters are deallocated from the stack. Remember, these are called automatic variables. So they are allocated. The space for these parameters and local variables are allocated when we enter the function, and they are deallocated. They are removed from the stack when we return from the function. Now that we have returned back into the context of sum 3, there is no space for sum 1 and sum 1, sum 2, and sum 1, which have already been erased from the stack, right? So we are here. Again, sum 2 is 2, and we are going to continue. Sum 2 is 3. So partial sum in the context of sum 3 will be equal to 3. We are going to continue with the merge step that says partial sum plus n. So that would be 3 plus 3, that would be 6. So we return from the recursion into the context of sum 4. So the partial sum in the context of sum 4 will have a value of 6. The execution continues. It says return partial sum plus n. So that would be 6 plus 4, 10. And we now return to the context of the main function, which made the first recursive first call to function sum. And the value of x would be 10. And that's what we're going to print on the screen. We will now look at a new problem, computing n factorial recursively. Obviously, you can easily write a for loop or a while loop to compute the n factorial, which is equal to 1 times 2 times 3 times n. But we would like to write this recursively. We'd like to compute this using a recursive function. Look at the base cases. This problem has two base cases. If n is equal to 0, then factorial of 0 is equal to 1. If n is equal to 1, then the factorial of 1 is also equal to 1. So that means if the problem is very small, like the size of the problem is 0 or 1, we don't have to divide the problem any further, which we can just return the solution immediately without dividing the problem any further. Otherwise, if the problem size is bigger than 0 or 1, let's look at how we can recursively formulate it. So factorial n is equal to 1 times 2 times n minus 1 times n. You can easily see that in order to compute n factorial, you need to compute n minus 1 factorial first and multiply the result with n. So basically, we are creating a subproblem of size n minus 1, which is a smaller scale than the original problem of size n, but has the same structure. So the original problem structure is 1 times 2 times n minus 1 times n. The structure of the subproblem is 1 times 2 times up until n minus 1. So it's the same problem, but that has a smaller scale. So that means I can recursively compute n minus 1 and just multiply it with n to compute the result for the original problem. Here is the recursive function for it. So this is example 2.cpp. Here's our factorial function. It takes an integer n, returns an integer. We write the base code for base cases at the top as usual. Remember, it has two base cases. If n is equal to 0, return 1. If n is equal to 1, then return 1. So we can write the code for it as follows. We can say if n is less than or equal to 1, return 1. Obviously, I'm assuming that the value of n is never negative. So it's either 0, 1, or a bigger value. So if it is 0 or 1, which means n is less than or equal to 1, return 1. So 0 factorial is equal to 1, and 1 factorial is also equal to 1. Otherwise, we go into the divide and conquer step, where we say, what is the smaller subproblem that is of the same, that has the same definition as the original problem, but has a smaller scale, and that will be factorial n minus 1. So if we know the solution to factorial n minus 1, which we can easily compute recursively using the same function, because the size of the original problem is n, this is a smaller problem. So if factorial is computing the factorial for problems of size n, it must compute the factorial for a problem of size n minus 1. Once I have the solution to factorial n minus 1, the merging step is very easy. All I have to do is multiply the partial answer with n to compute the solution to the original problem. Let's look at the recursion 3 for factorial 4. We are again at the main, making a call to factorial 4. So that's the first statement we are going to execute when this program starts executing. We're going to say a factorial 4. So now we are inside the first statement of factorial. Obviously, 4 is not less than or equal to 1. So we continue and execute. Partial answer is equal to factorial 3. So that's our recursive call. But this time the value of the parameter is 3. So we again enter the factorial function. The first statement says, is it a base case? The answer is no. 3 is not less than or equal to 1. So we continue and execute the statement. Partial answer is equal to factorial n minus 1, which is 2 at this point. So that's another recursive call. We enter into the context of factorial 2, execute the first statement. Is it the base case? No. So we continue and execute the statement. Partial answer is equal to a factorial 1. Now we make a call to factorial 1, but this time this is the base case because n is equal to 1. So we hit the base case or the stopping condition. and just return the value of 1 as the result of factorial 1. So this is going to return me 1, and now I'm going to return from the recursion, backtrack into the context of factorial 2 and assign 2 1 as into the partial sum. I'm sorry, partial answer. And now the execution continues with the merge step that says partial answer times n. The value of n is 2, so it's 2 times 1. That would be, I'm sorry, 1 times 2, that would be 2. Now we return back to the context of factorial 3. Partial answer would be 2, and we continue with the merge step that says partial answer times n, so that would be 2 times 3, that's 6. We return to the context of factorial 6. The value of the partial answer would be 6, and we continue with the merge step that says partial answer times n. Partial answer is 6, factorial n is 4, so the 6 times 4, that's 24. Now we are we return into the context of main, where we just print the value of 24 on the screen. And here is the call stack for factorial. So initially we are inside main, so we are making a call to factorial 4, and that when we make a function call, the space for arguments, so the parameters of the function and the local variables will be allocated. So we'll be into the context of factorial 4, a function invocation frame or call frame is allocated for factorial 4 with the parameter value being 4. Partial answer is undefined at this point, but we are making a recursive call to factorial 3. So that's another recursive call. That means the space for function called factorial 3 will be allocated, which is a parameter which n with a value of 3 and a local variable partial answer. Again, this is not the base case, so we'll make another recursive call, this time space for factorial 2. A function invocation frame for factorial 2 is allocated. Again, this is still not the base case, so we make another recursive call and enter factorial with a parameter value of 1. Still space for n, the parameter, and the local variable is allocated on the stack, which means n is 1, partial answer is undefined. This is the base case, so now we return 1. And when we return, the space for factorial 1 is deallocated from the stack. We are now in the context of factorial 2. The value of the partial answer is 1. We continue and execute the merge step. It says partial answer times n. So partial answer is 1, n is equal to 2. We are going to execute 1 times 2, that's 2. And we now return from factorial 2 into the context of factorial 3, assigning the return value into partial answer, which is 2. Now continue executing the merge step that says partial answer times n, so it's 2 times 3, that's 6, and we return into the context of factorial 4. Partial answer, the value of the partial answer is 6. We continue with the merge step that says partial answer times n, so that's 6 times 4, that's 24. Now we are within the context of main, and we print the value of 24 on the screen. Here is the actual code that implements the factorial function recursively. So we've got, the first call that I'm making into factorial is with a value of 4. So the argument that I'm passing into factorial is 4. I would like to compute 4 factorial, basically. Again, this is my template. Remember our template call for recursive functions. So you've got a recursive function that takes a problem of size n. We write the base cases at the top. So the base case is if n is less than or equal to 1, return 1. Again, I'm assuming that n is never negative, because if it is negative, this is not going to stop. So I'm assuming that factorial is always called with a value of n that's either 0 or more. Then otherwise, I'm going into the divide and conquer step. I'm saying what is the smaller subproblem that I can solve using recursion. And the subproblem is n minus 1, of size n minus 1. It is the same subproblem, but has a smaller scale. So if I call factorial with n minus 1, I'm going to get the factorial of n minus 1. And in order to compute the n factorial, given n minus 1 factorial, all I have to do is multiply the partial answer with n. That's it. That's very simple. The merging step is very simple. So let me just execute this so that you see that we actually get 24 on the screen. As you can see, the factorial of 4 factorial is equal to 24, and you can change n and obtain the factorial for other numbers. So let's do 5 factorial, that should be 120, and so on. So for the time being, this is all we have as far as recursion is concerned. If you have any questions, leave them in the comments section.